The last big idea that we're going to deal with functions in this class is the idea of functional composition. We've already briefly talked about that before when we looked at function machines, and we talked about taking the output of one function as the input into another function. The official definition here for functional composition and the operator, which is a circle, says if we have a function that goes from x to y prime and a function g going from y to z, they are functions that have a particular property that the range of the f function is a subset of the domain of the g function. Okay, that makes sense because one has to, what comes out of here has to be something that's able to go into, what comes out of one function box has to be able to go into the next function box. That's why we have that property that way. And what we're going to say is that f circle g of x, or no, they've done g circle f of x, says g of f of x for this is going to be a function of a function. So what we're doing here is we have a function g that takes these results of the function f and maps them to the final location. Let's look at this with something a little more concrete, with some examples. Okay, we're going to look at composition of functions. We've said that f circle g of x means we're taking f of g of x, and g circle f of x says we're taking g of f of x. Let's make up two functions here. F of x is going to be a linear function that says 2x plus 1. G of x is this squaring function. So if I looked at some examples here, f of 3 Sorry, let's get the light right on this. F of 3, we're going to put 3 in where we see x here. So it's going to be 2 times 3 plus 1. This is 6 plus 1, or 7. G of 3 is going to be 3 squared. 3 times 3 is 9. F circle g of 3 is f of g of 3. Well, g of 3 we already found is going to be 9. And if we then run that through the f function, we're going to have 2 times 9 plus 1. 2 times 9 is 18 plus 1 makes that one 19. If we do the functional composition in the other direction, this is g of f of 3. Well, we already did f of 3, found it to be 7. And when we take g of 7, we're squaring it to get 49. So let's do this in general. What is f circle g of x? It's f of g of x. G of x, we said, is x squared. And if we take that and run it through x, run it through f, we're going to get 2 times x squared plus 1. On the other hand, if we do g circle f of x, we're taking g of f of x. F of x is 2x plus 1, and we're going to run that through g, which is going to give us 2x plus 1, the quantity squared. And if you want to square that with FOIL, you can do that. Notice that you could use the same function each place. So this is f of x. F of x is 2x plus 1. And if I run that through f, I get 2x plus 1 times 2 plus another one. Oh, let's extend this down a little bit. That's going to be 4x plus 3. 2 times the 1 is 2, plus another one is the 3. What if we do circle g of x? We're doing g of x. G of x, we saw, is x squared. And when we square that, we're getting x to the 4th. So this is the basics of doing functional composition. Hey, let's look at one other thing here. We looked at, before, inverse functions. Looking at our function up here of f of x is equal to 2x plus 1. F of x, again, is equal to 2x plus 1. What is the inverse function for that? Well, what we did before is we said y is equal to 2x plus 1. We can interchange the domain and the codomain. X is equal to 2y plus 1. So that means 2y is equal to x minus 1. So x is equal to x minus 1 over 2. That's our inverse function. Now what I'd like you to see is what happens if you take f, circle f inverse of x. Well, f inverse of x is x minus 1 over 2. And if I take this and run it through the f function, I'm going to take 2 times this and add 1. The 2's here cancel. I get x minus 1 plus 1, which is just x back, which we know now is our identity function. What if I do it the other way and I take f inverse of f of x? Well, this is f inverse of f of x. F of x, we said, was going to be 2x plus 1. And if I do the inverse of that, I get 2x plus 1 minus 1 divided by 2. These cancel out. I have 2x over 2. I get x again. So the interesting property that we get here is that f inverse circle f of x is the same thing as f circle f inverse of x, which is always going to be the identity function.